SwayamPrabha. Digital India. Educated India.
In the previous class, I was talking about fully resolved approach for modeling two-way coupled flows. So, in this case, the flow around individual particles must be resolved, and because of this reason, this is computationally expensive and almost practically impossible for engineering flows. However, such approach is useful in gaining physical insight into the problem and to develop new models. We have already discussed this. So now, what is the way forward if we cannot use fully resolved approach for practical cases? Let's see that. So the other approach is volume averaging. So what is meant by volume averaging? So because we know that the particles are distributed throughout the flow, so it's a natural choice to divide this entire region into finite volumes and consider the particle behavior in each volume. So and we write equations for each grid. That is the idea. So in this case, we basically overlap a grid on the multiphase flows, where this is the grid volume, and within each grid we have particles, certain number of particles, and L represents the separation distance between particles. So now the question is there any limitations on the size of the grid that we can choose? What factors decide the grid size? Because if it is too small, we have issues. So basically you consider the case where the grid size is too small and smaller than the particle itself, then it tends to be the fully resolved approach. So we again have the same problem. If it is too large, then we miss out the information because the information is averaged out within a grid. So in general, the criteria to select a grid's size is such that the volume of the grid is much larger than cube of the interparticle separation distance. Okay. So which represents basically the effective area around individual particle. So the grid size should be much larger than the effective area around individual particles. But at the same time, it must be also less than the characteristic size of the flow. So what does this mean? The characteristic size. For example, let's say you are considering the flow, particle laden flow in a channel, then the channel height is the characteristic dimension. If you are considering the behavior of particles in a jet, then the radius of the jet or diameter of the jet is a characteristic length. So the grid, if the grid size is comparable to the characteristic length, then you lose out the information because that is averaged out. Okay. However, if it is too small, we have another issue also. If you remember earlier, we had discussed the definition of, for example, particle number density. When we discuss this in the context of continuum approximation. Okay. So if the grid size is much smaller, then another problem is that always we will have fluctuations in the particle number density. Okay. So we have to ensure that the particle's number density does not vary much within a grid. Okay. So for now, if we consider the limit of this variation of the number density to be about say 5% at 95% confidence interval, it can be shown that the cube root of this particle of this grid volume should be of the order of 18 times the interseparation distance. So how do we get it? Through another analysis, through a theoretical analysis. So this is how, so if we maintain this, so if the grid size is of this order, then that ensures that you don't have variation in or fluctuation in the particle number density because of the choice of the grid. Okay. So it is like, let's say, the definition of density, fluid density. Let's say you have a single phase flow, as we had discussed earlier. So what is density? Mass of, let's say we are considering a gas. So mass of a gas per unit volume. Now if you choose your volume to be very small, which scales with the mean free path of the molecules, then obviously you will have fluctuations of density. So density means what? Mass of number of molecules divided by the volume. So if the volume itself is small, then you will have fluctuations in the density itself, which we usually treat this as constant, because our region of interest is much larger than the mean free path of the molecules. So that is the reason why we can treat density as constant under continuum assumption. So this is also something along that line you can imagine. So the grid size should be selected such that we have minimal variation in the number density. So here you see that this is the size of the grid is about 20 times the separation distance. So now if we consider, for example, 20 micron water droplets in air with volume fraction of 0.01 as an example, then we can calculate the normalized separation distance from the volume fraction. We have done this earlier, and this turns out to be 4. So for this kind of loading, the particle separation distance is about 4 times the particle size. Then according to this theory, the size of the grid should be about 72 times the particle diameter, because the separation distance is about 4 times the diameter. So this means that the grid size should be 72 times the particle size, which is about, let's say, in this case, about 1.5 mm. So this restricts the level up to which you can resolve a flow. You cannot resolve the flow below this limit. Okay. So now, what is actually meant by volume averaging? So by volume averaging, we mean that all the flow parameters are defined at the center of the grid and the parameters are volume averaged. This means that, for example, if you consider, let's say, velocity, fluid velocity, then basically we average the fluid velocity over this volume, or we take the volume integral of the fluid velocity. In simple word, you add up all the velocity in this volume, velocity at all points within this grid, sum them up and then divide by the total volume. So this is basically the volume averaged velocity, and we write the equations not for u but for the volume averaged velocity. But Is there any issue with that? The main issue is due to this. So here you see that now we are actually decomposing the actual velocity to the average velocity plus some deviation from the average. So this is similar to Reynolds decomposition in turbulent flows. We will look at that later again when we consider particle turbulence interaction. But this type of decomposition is similar to the Reynolds decomposition in turbulent flows. Now, similarly, we have to average other parameters, for example, all velocity components, pressure, temperature. But if we can assume fluid density to be constant, if we are considering flows with, let's say, very low particle loading ratio, let's say dilute flows, then that simplifies the analysis or the governing equations further. So now we will look at the continuity equation, and let's see how the continuity equation is modified because of the presence of particles. Earlier we have seen the continuity equation for single phase fluids, but when we have presence of particles and we have the coupling parameters important, in this case mass coupling parameter important, then how the equation is modified. So we can start with a one-dimensional flow. So here we consider one control volume here. Then we know that from mass conservation, the rate of accumulation of mass within this control volume plus the net efflux of mass must be equal to 0. So mass has to be conserved. So now if we write that in mathematical form, then so this is the mass of the carrier phase within this control volume, and its rate of change is given by this parameter. So this is the rate of mass accumulation plus the net efflux of mass plus, so this is the rate with respect to time. But if we consider that some mass of fluid is entering in this direction and it is leaving here, then the difference would also contribute to rate of mass accumulation. So that's what we have here. So rho, here I am writing bulk density, okay, because this is particle laden flows. So bulk density times the area, area means the projected area, times the velocity here. So this is your x location, this is x plus delta x. So you calculate the mass flow rate at this location minus mass flow rate at this location. Okay, so this term basically refers to rate of mass accumulation plus we have this term which represents the mass generation. Okay. If we have evaporation, then it is mass generation. If you have condensation, then mass is depleted. Okay. So basically we have sum up the contributions for mass from all terms, and now that must be equal to 0. So now simplifying this expression, we can show that the rate of change of this parameter rho c alpha c plus the gradient of rho c alpha c u, this is equal to minus 1 by v. So this is the volume times the sum of all mass generation terms. So and then in the limiting case we can get this equation, and finally we get our continuity equation. So here this term I denotes the coordinate directions, and here K denotes the particle index. Particle index means you may have, let us say, 100 particles, then K ranges from 1 to 100. Okay. So, here we are following Einstein summation convention, and so this means that here you are summing over this term ui xi. So, this means that here you have this u, first term is del u by del x, second one del v by del y, third one del w by del z. Okay. So, this is our continuity equation. So, now what we see here is that because of presence of particles, we have this source term. Okay. So, if the particles are not evaporating or condensing, let us say you use solid particles in isothermal flow, then this term should be 0 and you get back your continuity equation. Okay. Now, if the size of all particles are same, here, then we can write this term as the number of particles times the rate of change of mass of individual particles, but I can take the number term out and this will give me number per unit volume, that is the number density, that is what we have here. So, number density times the rate of change of particle mass. Yeah, so I have written here. Okay. So, now if we consider another case where we have basically low volume fraction, then alpha c tends to 1 and the bulk density is basically equal to the carrier phase density. So, we can incorporate that and you see what do we get. So, in this case, if there is no mass there is no mass exchange occurring between the particle phase and the continuous phase, then this term is 0 and we get back the continuity equation. Okay. Next, similarly we can have species equation. Okay. So, here also we have an source term, we have a source term. So, here in the species equation what do you get is, so I am not deriving again all the conservation equations, we can do it in a similar way as we did it for the continuity equation. So, in this case what does this term represent? So, this is the local generation of a species. This represents the convective transport of a species due to the flow velocity, and this represents the diffusive transport. Okay. And here we have the source term. So, how many equations we have here? The number of equations is basically equal to the number of species. Okay. So, here we are writing this equation for n species. Now, if you look at the source term, this looks similar to the source term what we have in case of the continuity equation. In fact, if we add up all the source term or if we add up all the species equations, we get the continuity equation only. So, we can visualize it better if we consider this simple example of water droplets in air. So, in this case how many species we have? 2. What are those? Air and water? No, air and water vapor. Here we are talking about species in the carrier phase, please do not get confused. So here we are talking about the species present in the carrier phase only. Droplet is a different phase for which we have separate sets of equations that we discussed already. So if we have air and water vapor, we have two equations for air and for water vapor. So this source term is present in which species? For water vapor, not for air. For air it will be 0 because there is no generation or depletion of air for this case where we have evaporation process present only. Okay. So in this case, the source term for the vapor is basically equal to the source term for the continuity equation, because the source term for the air is 0. But if we have more complex cases, for example, let's say combustion of fuel droplets, let's say combustion of diesel droplets, then initially what do you have? The reactants present, which means you have air and vapor of the fuel. But after the reaction, what are the species which are present? The products of combustion, which can be carbon dioxide, water vapor itself, let's say nitrogen oxides, let's say hydrogen, and so on. So we need to have, if we are interested in the concentration of the species generated from the combustion process, then that many equations we will have to solve. Next, we have momentum equation. So in momentum equation also, you see that there is now an extra term present. Now here you need to look at this bit carefully. So apart from this, you have this term present as well. Now why we have this? We have this additional term present in the momentum equation. Okay, so for a moment, if you assume that the volume fraction of the carrier phase is close to 1, left side you get basically what you have in case of Navier-Stokes equation. So this is basically the modified form of Navier-Stokes equation. Now here you have body force term, this is pressure term, this is the viscous term. But here, because of this decomposition, here we have this extra term present, which is known as volume averaged Reynolds stress. This part, volume averaged Reynolds stress present. Now here I would like to remind you one thing, that although we are doing this decomposition and actually the equations are written for the average velocity, for simplicity throughout we are using this notation. We are using this notation U only, okay, for simplicity. But ideally these are all for, here everywhere you have volume averaged quantity, that we have to keep in mind. So now what causes this volume averaged Reynolds stress? So this type of term is present for when we do RANS modeling or Reynolds averaged Navier-Stokes modeling for turbulent flows. Now this is present because we have turbulence in the flow. But it is not only due to turbulence, we have also velocity deviation owing to flow around particles. So here the point is that, now let us say this is your grid and you have particles. So now because of the particle motion or relative velocity between the particle and the fluid flow, the flow field in this grid, within this grid, is not uniform. Imagine these particles are generating vortex shading. Vortex shading happens past all the particles. So that causes non-uniformity in your flow. Okay. And this, when you do this decomposition, you have this term present because of that. And obviously, if the flow field itself is turbulent, then this term will always be present. Okay. Next, we have this source term. So here, what contributes to this source term in the momentum equation? So here you have two terms. If you see the first term, this is due to the particle velocity. So the particles, let's say, are evaporating. We are considering again and again this case of evaporation for better understanding, but it's not limited to evaporation. Any type of particle mass generation or depletion can be accounted. So the particle is moving, it's evaporating, it's moving. So the vapor which is generated, that also moves at the particle velocity. So it's like, in this case, we are adding momentum to the carrier phase flow. So that is why you have this term. And why you have minus? Because this term m dot itself is negative in case of evaporation. So this parameter refers to the momentum coupling due to mass transfer. So we can, so if we have all particles with same size, then we can show that this is basically equal to the source term due to mass times the particle velocity. But we can neglect it if we find that the mass coupling parameter is, if you remember, we have already discussed mass coupling parameter. So if the mass coupling parameter is small, we can neglect this term. And in general, this rate is typically much smaller in practical cases, especially when you have very small droplets. Let's say you have 50 micron droplets. So the rate at which mass is transferred, okay, is usually very small. Next one is the most important term, that is due to the force exerted by the particles. So in the previous, in the earlier lectures, we have extensively discussed the forces on a particle, and it is not limited to drag. It can be due to undisturbed flow. It can be due to the virtual mass, added mass. So there can be various factors which contribute to force on a particle. But according to Newton's third law, the particle must exert equal and opposite force on the fluid, and that is what we have to account for, and that is what is done here. So here we are adding up the force due to individual particles, and it is normalized with the volume. So this is how the source term due to momentum transfer is accounted in case of particle laden flows. Next, energy equation. So in a similar way, we have a source term in the energy equation also. So here again, if you consider that the carrier phase volume fraction is approximately equal to 1, then the left side is essentially same as the single phase flow, and that represent the convective heat transfer. Okay. And this one is the diffusive heat transfer. However, there is a concern here. So this parameter lambda c here represents the thermal conductivity, but but it actually represents the effective thermal conductivity of the fluid and particle system together. And why this is so? Because of this. So again, here you see you have terms, this term here, basically this term. This is the product of the fluid velocity and temperature. But if we do volume averaging of this quantity, we get this. So what is written here is essentially this one. Okay, but you do volume averaging, so this operator refers to volume averaging. So you do volume averaging over this product, but it has some residual also. So now the question is, how do we model this? So this has been already accounted in this model. So that is why what you see here is the effective thermal conductivity of this fluid particle system together. But the form up to this, the form looks similar to the single phase flow energy equation. But here we have a source term because of the presence of particles. And that source term again has two components. First one is due to enthalpy of the vapor in the case of evaporation process, for example. So you are adding enthalpy to the carrier phase. If the particles are evaporating, you are adding enthalpy. The vapor which is getting mixed with the air, that has some enthalpy. So you are adding enthalpy. So that we have to account for. And then you have this term, which is again the most important term here in this source term, that is the heat transfer from the particle. So if the particle is losing heat, then this means that the carrier phase is gaining the heat. So that is why we are adding this. Okay. So now the question is, there are so many forces that we have discussed which are present on a particle. So how do we now model all those processes in this volume averaging approach? It will be difficult to account for all the forces and accordingly the heat transfer terms also. So we need some simplification. So for that purpose, this is a model called point particle assumption, which is widely used in multiphase flows, especially where the dispersed phase is much smaller than the characteristic length scale of the flow. If you are considering very small particles, for example, let's say you have you are considering particle flow in a channel, and the channel height is, let's say, 0.5 meter, and the particle size is, say, 1 to 100 micron. So this means that the particle size is much smaller than the characteristic length scale. So in those cases, we can use this. For example, let's say you have very small bubbles, say micro bubbles in a liquid. Okay. Then also you can use it. Now in this case, what is the idea behind this type of model? In this case, we treat each particle as a point with no finite size. So what is meant by this? So you have a particle, you imagine you have a particle in the flow, but it does not have a finite volume which is occupied in space. It is considered as a point. You account for all the forces, you account for all the heat transfer, but you assume that it is physically not occupying any space. So what does that mean? That means that, let's say you have a particle here, okay, and it is moving in the flow, then it can create its own vortices, and you can also have vortex shredding phenomena. Okay. But if you assume that such phenomena are absent, then you can consider only the drag force on the particle, for example. So, here what you need to do, you need to account for this force exerted by the particle on the fluid and also by the fluid on the particle. But if the particle size is very small, or if you assume that it does not occupy any space to create such kind of phenomena, then your modeling assumptions simplifies the problem. So, in that case, you can consider that, okay, I have only drag term present and only gravity term present. That is why this is useful when the size of the particles bubbles are much smaller. Okay. If the size of the particles and bubbles are larger, then you can have this kind of effect. And in case of bubbly flows, for example, you can have the virtual mass term or the added mass term also becoming important, or the undisturbed flow term. All these factors will become important. So, in this model, we basically neglect the volume of the particle. Then the particle basically interacts with the flow only through forces and heat transfer, but it does not directly disturb the flow field around it, as it is the case in case of finite object would be, for example, this. Okay. So, basically the particle itself does not modify the flow because of such phenomena like vortex shedding. So, this is known as point particle assumption, and this is a very popular model in the numerical simulation of the multiphase flows. But what are the conditions for validity for such models? So, as I mentioned, the particle diameter must be smaller than the smallest relevant fluid length scale. We will again discuss this when we talk about when I talk about turbulence, but Kolmogorov length scale represents the smallest scale in a turbulent flow. So, this assumption of point particle is valid when we have the particle size smaller than the smallest length scale, that is the Kolmogorov scale. And if we have a laminar flow, then the particle size must be smaller than the characteristic scale for velocity gradient. This is the scale over which you have a strong velocity gradient. Okay. So, the particle size is much smaller than that. Then the other condition is that the volume fraction of particles is small. So, typically we have dilute region. So, when you say you have dilute region, then the volume fraction is basically less than 10 to the power of -6. Okay. So that why we have this condition? Because in this case we can neglect particle-particle interaction. So, physically when two large particles collide, they actually modify the flow field within them. So, this is the situation when we have four-way coupling region. However, in this case the particles are small. Still, through suitable model we can account for the collision effect, but as such physically there are no collision happening. And also the disturbance fields of individual particles don't overlap significantly. What is meant by again disturbance field? So, again, as a particle moves in a fluid, it creates disturbance in the fluid. For example, let us say some particles are moving in a stagnant ambient condition. Still locally it creates disturbance in the fluid flow. If you have large number of particles, then this disturbance will get amplified. So, that is why we have this assumption that you have very low volume loading or you have a dilute flow, then point particle assumption is more valid. And finally, the Reynolds number of the particles relative Reynolds number of the particle relative motion is small enough to justify simplified drag correlations unless empirical correlations are introduced. So, imagine the particle is smaller than Kolmogorov scale. So, in that case, the relative velocity between the particle and the fluid will be small. Why? Because in this case, the Stokes number is expected to be small. It need not be small, but is expected to be small enough. So, this means that the relative velocity is not high. So, if we calculate, for example, the Reynolds number of the particle, how do you calculate Reynolds number of the particle? Rho relative velocity d by mu. So, if you calculate Reynolds number of the particle, this will be of the order of 1 such that Stokes drag is valid. So, once Stokes drag, you know that Stokes drag is valid, you can use Stokes drag law and model the drag force. Otherwise, also it is possible to account for the finite Reynolds number effect, as we have discussed, if you remember, through the correction factor, that we can account for it. However, if the particle size is too large and that causes vortex shading, there is no model which can correctly account for that. So, for such cases, if the particle size is large, we have to adopt fully resolved simulation approach only. What are the advantages and limitations of the point particle assumption? So, the main advantage here is that it is computationally efficient. Why? Because we do not have to resolve the flow around particles. Then it is applicable to large number of particles so that we can deal with engineering type of problems. Okay. And this facilitates basically simulation of the particle-laden flow in Eulerian Lagrangian framework. What does that mean? That means that if you see the conservation equations that we have seen, it is Eulerian for the fluid phase or the carrier phase, but it is Lagrangian for the particle phase. Okay. Then, in spite of its limitations, it captures the essential physics, for example, momentum exchange, heat transfer for dilute flow. So, this is basically the bottom line. So, as long as you have dilute flows, even it can handle two-way coupling up to some extent. So, which means that say this is up to 10 to the power of minus 5 or 10 to the power of minus 4, we can increase it. It captures the physics behind the particle fluid interaction. But where are the limitations? The limitations are the following. So, first of all, it will fail if the particle size is comparable to or larger than the flow scales. It will not work in that region. So, now the main problem here is that you can still do a simulation. Even if the particle size is large, you can still do a simulation, but it won't physically be, it won't give you any physically correct result. And as I said, it cannot resolve these effects like wake formation, vortex shading, and of course, it requires modeling the drag, lift, heat and mass transfer, unlike the fully resolved approach. So, if you fully resolve a flow, you do not have to model, for example, drag. You do not need any drag model, for example, Stokes drag model, because you are resolving the boundary layer around individual particles. So, you calculate the force directly. You do not have to use any model, but in this case, you will have to model, you will have to use the models, and you are restricted by the assumptions in the model. For example, Stokes drag is valid only for certain range of Reynolds number. And as I said, it is less accurate in dense regions where particle-particle interactions come into picture. So, for example, fluidized beds where you have really dense loading, where the volume fraction is of the order of 10 to the power of -3. So, in such cases, the Lagrangian particle tracking using point particle assumptions should not be used. Another example is very close to an injector. Very close to an injector which generates a spray. The volume loading is very high and particle-particle collision is very much possible. So, it should be avoided in that region. Okay. So, we will stop here. We will continue this in the next class.